Hi, my name is Andrew Rouditchenko. I'm a PhD student at MIT, and today I'll be presenting my work, Comparison of Multilingual Self-Supervised and Weakly-Supervised Speech Pre-training for Adaptation to Unseen Languages. There are thousands of spoken languages in the world, and automatic speech recognition, or ASR, should ideally support all of them. Given the need for labeled data, ASR has been historically developed for high-resource languages, but this is changing. New multilingual models support hundreds of languages thanks to more data and more compute. This is a list of multilingual models released in the last 3 years. These models were trained on hundreds of languages. They're mostly open source, and self-supervised learning helps leverage unlabeled data. In this work, we'll focus on the XLSR and Whisper models, which were available at the time of this work. XLSR and Whisper are great, but they still omit several thousand spoken languages from training. And many of these unseen languages are sufficiently widespread to be of interest. For example, they have over 1 million speakers. More data like Common Voice and new models are mitigating this problem. However, they still don't support all languages. It's easier to, and this is partially because it's easier to acquire unlabeled data than labeled data. So we consider it important to be able to adapt to unseen languages. This work, we're going to consider some of those languages like Oromo, and we're going to compare Whisper and XLSR on those languages that they weren't trained on. XLSR follows a self-supervised learning strategy where it first optimizes a proxy task on unlabeled data, for example, mass reconstruction, and then it fine-tunes on labeled data. And it can be fine-tuned separately on each language or in a multilingual fashion where we fine-tune on multiple languages at the same time. And this makes use of unlabeled data, but it requires fine-tuning with potentially different hyperparameters on each data set. Whisper, on the other hand, just has a single step of being trained on labeled data in a multilingual fashion. This directly optimizes for the downstream task. For XLSR, the SSL pre-training was done on 53 languages at first, but then it scaled up to 128 languages. And the more recent model leverages 436,000 hours of unlabeled audio. For Whisper, it's a supervised model trained on 680,000 hours of labeled audio in 99 languages, and it can perform zero-shot ASR, which means ASR without fine-tuning on different data sets. So in this work, we're going to ask which model adapts better to unseen languages. Specifically, if we acquire labeled data in a new language, which model is going to perform better? Our approach is to fine-tune both models on each language separately. And first, we're going to fine-tune on 18 seen languages separately. So they were trained on those 18 languages. Then we're going to try them on 13 unseen languages, so languages that they weren't trained on. And our main result is that the number of hours seen per language and language family during pre-training is predictive of how the models compare. This is even though the models and pre-training methods are very different. So here we show the pre-training distribution per language family for Whisper and XLSR. We can see that Whisper was trained on more hours in high resource language families versus XLSR was trained on more hours in lower resource language families. For the experimental setup, the goal is to make the comparison between XLSR and Whisper as fair as possible. We use the Floors data set first for unseen languages, and this data set has 102 languages where the text was originally in English and then translated to other languages, and it's speech that is read, and it's approximately 10 hours of data per language. And neither XLSR nor Whisper included this data set during the pre-training, and there are 13 unseen languages in common to both models. These are the languages, and we can see that they're from different language families. We also use Common Voice 11 for unseen languages, and this has over 100 languages. The data set itself, it's text sourced from the internet. It's read speech where the number of hours varies, and Whisper was not trained on Common Voice while XLSR was trained on other languages in Common Voice. So XLSR might have an advantage over Whisper here since it was trained on audio in the same domain. And there are 12 unseen languages in common to both models. This is a list of the unseen languages, and we can see that the number of hours per language varies. For the seen languages, we use the Floors data set. We have two categories of languages. The first is where Whisper has seen significantly more hours. And for these languages, for example, English, Whisper has seen approximately 400,000 hours, while XLSR has seen around 70,000 hours. For the second group of languages, XLSR has seen far more hours. For example, in Czech, XLSR has seen 18,000, while Whisper has only seen 192. For model sizes, XLSR is a transformer encoder with a linear decoder. And there are different model sizes, 3 different model sizes. For Whisper, it's a transformer encoder decoder, and there are 5 different model sizes. In this work, we focus on the 2 smallest XLSR models and the 3 largest Whisper models. And this is mainly because the 2.16 billion XLSR model was too big for our compute. For the tokenization, for XLSR, we used language-specific characters where we initialize a linear layer from random for each language. And for Whisper, we use the byte-level BPE tokenizer, which can encode any text, so there's no auto-vocabularies. However, the encoding is potentially inefficient because one character could be mapped to multiple tokens. For Whisper, it expects a language token in the decoder output, but this can be manually specified. For the unseen languages, there isn't a token because it wasn't trained on those languages, so we set the token equal to a language similar to each unseen language, or we set the token equal to English. And both strategies work similarly, so we just use English as a language token for each unseen language. For decoding, we did it without a language model so that the results are independent of external modules, and since Floris contains little text to train them, the main results are reported with greedy search. And for we tried beam search, and XLSR doesn't improve, while Whisper improves slightly. For the evaluation, we use character error rate since some languages don't use regular spacing. And we also report results for word error rate in the paper, and the trends are consistent with character error rate. For the text normalization, since Whisper was trained on unnormalized transcripts, they introduced a multilingual text normalizer to standardize both the Whisper transcripts and the evaluation transcripts. So we applied this Whisper normalizer to all model-generated and all ground truth transcripts during evaluation to make a fair comparison against all models. Okay, we'll start with the results for the seen languages. We'll first show that fine-tuning Whisper improves the performance. Then we're going to compare XLSR and Whisper against each other in both categories of languages. And then we're going to predict which model will do better on a given language using linear regression. So first off, fine-tuning Whisper improves the performance. Here we show that after we fine-tune Whisper small, the performance tends to get better, meaning a lower character error rate. And this is true for all the languages except for English and Korean, so it got slightly worse there. And we get a huge improvement for lower resource languages where the model was basically unusable, but then once we fine-tuned it, it could get acceptable character error rates. And same trend for Whisper medium and Whisper large, where there's might be one or two languages where it gets worse, but generally get a large improvement after fine-tuning. So now comparing XLSR and Whisper, we first compare them on languages where Whisper saw far more hours of training data. And these are the results for all 5 models that we're comparing. And when Whisper has seen far more hours than XLSR, even the smallest Whisper small model outperforms XLSR. So it shows that the advantage of being trained on so much data in those languages. When the amount of training data becomes more similar, then we have that XLSR larger model starts to outperform Whisper. Okay, next we'll show the results where XLSR has seen far more training data than Whisper. And here are the results again, and we find that the smallest XLSR model can outperform the largest Whisper large model. And when the amount of data becomes more similar, the models tend to perform similarly. So far, we have that the number of hours seen per language seems to be predictive of how the models compare. And so we're going to try to predict which model will do better on a given language using linear regression. Here we show a plot comparing XLSR base to Whisper small, 244 million. And each point shows a different language. On the x-axis, we have the log ratio of their relative number of pre-training hours. So on the right side, we have XLSR saw more hours of data for that language. On the left hand, we had that Whisper small saw more hours of that language. On the y-axis, we have the relative performance. So the red line means equal performance. Above that means Whisper small performed better. Below that means XLSR performed better. And so when we put the line of best fit in the plot, we see that there's a slight bias towards XLSR, which is the larger model. It means that XLSR is performing better most of the time. However, the line of best fit is predicting that Whisper small will outperform XLSR when it's seen at least 3.5 times more data. So that's pretty useful as a predictive tool. We also repeated this linear regression with Whisper medium, and we see that now there's a slight bias towards Whisper medium, which in this case is the larger model. And now the line of best fit says that XLSR is going to outperform Whisper medium when it's seen at least 9.2x more data. So using this technique, we can make a decision rule. If we're deciding between 2 different models and we have a given seen language, we can decide try to predict which model will perform better. So the takeaways on seen languages is that fine-tuning Whisper improves performance even with just 10 hours of data. However, we didn't test catastrophic forgetting of the other languages. And for a Whisper versus XLSR, which model is better? It depends on the relative number of hours seen during pre-training. However, we can predict which model will do better in advance. Okay, so we're going to show the results on unseen languages now. So we're first going to compare XLSR and Whisper on unseen languages in different language families. We're going to show Indo-European languages first, where XLSR and Whisper have been pre-trained on similar number of hours. Then we're going to show other language families where they've been pre-trained, where XLSR has been pre-trained on more hours. For the data sets, we'll start with floors and then go to Common Voice. So again, on Indo-European families, they've been trained on approximately the same number of hours. And when we look at the performance on 3 different languages, the performance across the models is similar to each other. So when we go to the language families where XLSR has seen far more hours of, then we start to have that XLSR outperforms Whisper large. So even the smallest XLSR model gets better performance than the largest Whisper model. So XLSR seems to have a clear advantage. So it seems that the number of hours seen per language family is predictive of how the models compare. Also to note, the character error rates for the unseen languages are reasonable. For the seen languages, it's 8 versus 13 for the unseen languages. For the word error rate, it's 16 versus 40. So we get an acceptable kind of performance on unseen languages, probably due to the multilingual pre-training. So next we show the results on Common Voice. So here we're showing the unseen languages on Common Voice in the Indo-European language family. And here XLSR is outperforming Whisper medium on all languages except for this one. And when we look at the other language families where on some of these language families, Whisper has seen far more data, we still have that XLSR is outperforming Whisper medium on all of these languages except for one. So here it seems that XLSR has an advantage and it's outperforming Whisper on most unseen languages in Common Voice. And we think this is possibly since XLSR was already trained on other languages in Common Voice, meaning it was the same domain. And neither model was trained on languages in floors, so we consider it to be an unseen domain. So in conclusion, we aim to compare XLSR and Whisper on languages that they weren't trained on. We started with seen languages where we found that the number of hours seen in for that language is important to compare the models. And given a seen language and 2 models, we can predict in advance which one will get better performance. For the unseen languages, we found that the number of hours seen in the language family is important. However, we acknowledge that using language families as a predictive tool has limitations, so future work should study other factors. And also for Common Voice, it seems that there's a confounding variable potentially, which is that XLSR has already seen that domain. So thanks for your attention. Feel free to contact me with any questions.